In this video, we're going to take a look at set theory, which is the branch of mathematics which deals with collections of things. Now, these things can be anything. It could be numbers. They could also be the actors and actresses who've been in movies with Kevin Bacon. Or they could even be the set of cat emojis. Set theory is general in the sense that it doesn't matter what the elements of the sets are. Now, let's take a step back briefly to look at a few branches of mathematics at a high level so that we can put set theory into context. I'm sure you're familiar with algebra, which is the branch of mathematics that deals with variables, which are represented usually by letters and their values are free to vary. In geometry, we're concerned with shapes in a space. And naturally, we talk about the relationships and rules that govern those shapes. In set theory, like I said, we're dealing with collections. And just like in algebra and in geometry, we're going to have a set of ground rules and notation so that we can talk about these things. At the most basic level, we need a way to represent the sets themselves, and this will be done with curly braces. So we can define a set S, which is equal to, and we'll go ahead and write out our curly braces, and we can just give this some elements, let's say 1, 3, and 5. Now, I should note here that in set theory, order doesn't matter, so we could have arranged these in any order. We could have had 3, 5, 1, and this would have been equivalent. And additionally, you cannot have repeated elements in a set. This leads us to the membership symbol, which we can use if we want to express that something is an element of a set. So if we have this set again, S, we can say that 1 is an element of S. We could also say that 2 is not an element of S by using the same symbol with a line through it. Now let's look at a symbol which will be used to compare two sets to each other. And that's going to be the subset symbol, which looks just like the membership symbol, but without the line in the middle. So on the left-hand side this time, we're going to have a set instead of an element. So we can say S2 is a subset of S1. And what this means is that every element in S2 belongs to S1 as well. So 1 is present and 5 is present. Now additionally, we can say that S3 is a subset of S1, right? Because every element in S3 is present in S1. But to distinguish between these two types of subsets, because look, S3, every element is represented in S1 as well. So how you should write this is with a line under it, which just means, with the line under it, it basically means that, yes, S3 is a subset of S1, meaning that all of the elements in S3 are in S1. But without the line under it, in this case, S2 is a proper subset of S1, because while all of the elements in S2 belong in S1, not all of them are represented. So let's look at that last statement that we just had, where we said that S3 is a subset of S1. Now, this might seem a little weird to say because, well, we're dealing with two well-defined finite sets, and we can just look and see that they're equivalent. Because remember, we said that in set theory, order doesn't matter. So, well, another thing that we can say, we can add another statement to this because, yes, S3 is a subset of S1, but also S1 is a subset of S3. Because all of the elements in S1 appear in S3 as well. So whenever you have both of these statements together, it actually confirms your intuition, and you can redefine this double relationship as equivalency. So if the first set is a subset of the second set, and the second set is a subset of the first set, then that means the two sets are equal. So equivalency in set theory just means that all of the elements are present in both sets. And finally, we're going to look at a symbol which is not a comparative symbol like we've been looking at, but will actually yield a new set, and those are the union and intersection symbols. So if we have these two sets, S1 and S2, we're going to say that the union, which is represented by a U, which is a good way to remember union, so the union of S1 and S2 is going to be equal to all of the elements in either set. And of course, we're going to eliminate duplicates though. So 1 exists in either set, 3 exists in either set, 4, and 5. So it basically just makes a larger set, or equivalent size set, that includes any element that's present in either of the sets. Then we can look at the intersection symbol. So let's take the intersection of S1 and S2. And you can kind of remember that because this is going to be how we just looked at union, which was or. Intersection is going to be and. So this upside down U kind of looks like an A for and. So now we're only going to pick the elements that are in S1 and in S2. So the intersection is just going to be 1, 5. So we just saw a lot of notation for set theory. We covered the curly braces, which are used to represent sets. We saw the element of symbol, the subset symbols, the equality symbols, and the union and intersection symbols. If you're fuzzy on any of these, I recommend going back and rewatching the notation section. Also, I want to really quickly throw in something I didn't mention yet, which is the concept of the empty set. All of the sets we've looked at so far have had elements, but you can have a set that doesn't have any elements at all, and this is called the empty set. It can be represented by 2 empty curly braces or a 0 with a line through it. So we'll definitely see the empty set moving forward as well. Another kind of set we need to look at are nested sets. So far we've seen sets that have numbers as their elements. We've also seen a set called the empty set that doesn't have any elements at all. But remember, I said the elements of a set can be anything, and sets are things. So the elements of a set could be other sets. So this set, S, has 2 elements, and each of those elements are themselves sets with their own elements. Now let's talk about power sets. Say you have 3 friends whose initials start with A, B, and C, and you want to know all the different ways you could set up a dinner party invitation using those 3 friends. Well, the result would be the power set of your set of friends. So the power set is usually represented by kind of a scripty looking P as applied to S. And so the first way that you could set up an invitation is to invite nobody, which might be kind of a boring party, but maybe you don't really like your friends. Then you could just invite one friend. You can invite friend A, or you can invite friend B, or you can invite friend C, and all of these would be valid invitations as well. Or you can invite 2 friends. You can invite A and B. Maybe C doesn't get along with them. Or you could do B and C, or you could also do A and C. Or if everyone really got along splendidly, you could also invite everyone. So this big set, which consists of 8 sets, is the power set of S, which was the set that had 3 elements. So now I want to talk about how we can figure out the size of the power set of S if we know the size of S. So remember, when we were generating all those subsets for the power set, basically each time we were asking the question, should we include A, yes or no? Should we include B, yes or no? And should we include C, yes or no? Which is a binary question. And we use this to make all the different permutations that were the subsets of the power set of S. So since this is a binary question, we know that the resulting power set is going to be 2 to the power of the size of the original set. In this case, we have 3 elements in the original set, and 2 to the 3 is 8, which is exactly the size of the power set that we found. And finally, I want to talk about bijections between 2 sets. Now, bijection sounds like a scary word, but it really just means that you can define a mapping from one set to another where all of the elements are accounted for. So if we have set 1 and set 2 here, we could say, map A to F, map B to E, and map C to D. And since all of the elements in set 1 are represented in the mapping, and all of the elements of set 2 are represented, and there's no duplicates, we can say that the sizes of S1 and S2 are equivalent. So that covers the basics of set theory. We'll use a lot of this stuff in the next video where we look at infinite sets and some really cool things you can say about infinity when you use these tools of set theory. So I hope you join me there.